today. I'm going to have to go fairly quickly, but I hope we can cover it. And that is to do with scheduling. Okay? There's a few key take-home messages I want you to get from scheduling. I love it if you folks do scheduling. If you use the CPM diagram to lay out the dependencies between tasks and do schedules. It'll be incredibly useful for one or two reasons. Most importantly, it'll let you identify what's called the critical path of your project. This is essential. Critical path is going to be the pieces of your project, or of your next deliverable, say, that cannot be delayed without delaying the whole thing. In other words, if you delay them, it will adversely affect your ability to deliver on time. All the activities. There may be certain activities you have so-called slack on. You have leeway on. You have float on. We express it in different ways. Some activities, you don't have to keep on the ball about them. Critical path, you need to keep on the ball about it, because if it slips, it's going to delay the overall project, when the overall project completes. And if you can identify that critical path, it'll let you focus your efforts. It'll let you know what thing we need to just keep our nose to the grindstone, and what things we can kind of move people from because they're not as critical. So we've just been talking about estimates. And the estimates are great. They give a sense of task duration and effort. But they don't give a sense for a whole project, and not necessarily even for a whole deliverable. So if you naively just turn estimates into calendar dates, you just total up the estimates, you'll be ignoring some things. You'll be ignoring the fact that one dependency, for example, dependencies between activities, so one activity can't start until another one is finished. So for example, until the build server is set up, you're not going to be able to install the coverage testing framework, or you won't be able to install the issue tracking system. Until the test infrastructure is set up, you're not going to be able to perform tests. There are these dependencies. You can't do A before B. Also, if you have a bunch of estimates of tasks, task A is going to take 3 days. Task B is going to take, 4 days. You don't just want to total them up to figure out how much time the entire thing will take. Why not? Yeah, exactly. It depends a lot. So maybe the 3-day task could be started at the same time as the 4-day task, in which case the total time is just 4 days. It's the maximum of the two of them, right? You have them going on in parallel. On the other hand, if the 4-day task requires the 3-day task to finish, then you've got 7 days. Big difference. You appreciate that? So having estimates for tasks is fantastic. It's a great starting point. But to make sense of how long it is going to take in terms of calendar time, you have to think about these dependencies. What depends on what? What do we have to do before what? Does that make sense? Okay. Okay, so scheduling is going to allow turning many task durations into an estimate of project length. Okay. In the context of real projects, or projects in the external world, say in the commercial sector, it also allows for understanding cash flow. And it can have a material difference on how much value a company anticipates getting from a product. So why do we schedule? Well, there's two reasons. Actually, several reasons beyond this, but these are some of the two most important. It lowers the chance of delay. If you can be thinking through how long things will take, the things that you've got to get on the ball right now to finish, and what things can be left for later. And thereby you lower the risk of delay. But also, if you have a delay, it allows you to recover from that delay more effectively. It allows you to say, okay, what things do we have to attend to right now to still finish on time, for example. In larger projects, you can have a huge number of dependencies, potentially thousands of tasks. You think about a large project like Microsoft Office, all these pieces have to come together. And they have to be coordinated. You can't ship, you know, the updated version of Excel if the new version of Word that integrates with it isn't ready. Okay. So here we have to really take it seriously. What are these different components that have to be coordinated? Even for your tasks, you know, of length 3 weeks for your projects, there's going to be many tasks, some of which can be done in parallel and some of which can't be. Some of which depend on others. We have to get, you know, our test team lead has to create the descriptions of the tests before we can build the test matrix, before that matrix can be peer reviewed. So it kind of lays out, okay, how quickly can we get to that peer review, for example? Is it going to be faster to do by the end of the term? Okay, so a key thing we're going to be talking about here and emphasizing is the critical path. And I'm going to go through this quite quickly. Okay, I'm going to skip a lot of things here. There are some things in these projects you typically don't schedule, okay? Minor activities. When your uncertainty is really great about how long an activity timing is, for example, and it's at a very fine scale, it takes too much work to schedule it, and you just handle it dynamically. You just handle it, you know, for example, who takes on a given task often isn't pre-assigned. It depends who happens to have finished their task in, you know, at the appropriate point, and they grab it from a queue. That you just maintain this dynamic queue. So scheduling is not used for all things. I don't expect everything to be scheduled, but I do expect each team will do some basic scheduling for the big things that got to get done, for the big tasks that confront you. Now, how many people in this room have either seen or worked with Gantt charts? Nobody. Wow, that's interesting. Each year we typically have a few people. These are extremely common in industry. Maybe you've seen them before and not known what they are. Have you ever been to an architect's office who's involved in a construction project, or if you've been in larger software projects, you'll sometimes see things on the wall that look like what's on the screen. They're shown in different forms. Sometimes they have large bars like this, and often the bars are sort of going down here, upper left to lower right, and along the x-axis is time. So this might be, you know, beginning of the year, end of the year, and it's showing which activities are underway at a given time. So you consider a given time here, and it tells you what things are going to be underway at that time. Has anyone seen that before? Picture of that? Okay, you've seen some pictures of it. And this is really useful. Tasks here on the left, going down, time on the right, on the top of it. Okay, and this shows from when to when things are going to be underway. Okay, so when we're going to be doing what, and that's great. But we're going to be focusing on what are called CPM diagrams, critical path method diagrams. Okay, Gantt charts actually predate them. Gantt charts go back to World War I. They're extremely effective communication tools. You'll find virtually everyone in industry is going to be comfortable reading a Gantt chart. Okay, that's true in the software industry. It's true in the IT industry. It's true in lots of different areas. So commercial software development as well as IT within other types of companies. They're just extremely common. Managers use them a lot. They're very popular for representing simple data. The key shortcoming, and I expect you to know this, folks. This is like prime pop quiz material. No, don't worry, it's not on the end of the class pop quiz. How do you get that pop quiz at the end of it? We would let people come in and see if you absorbed it. Wow, okay, that's an interesting idea. Wouldn't disturb the meeting. Okay, the main shortcoming here is no dependencies are captured. That's the problem with the Gantt chart. It doesn't tell me, for example, hey, if I delay this activity here, does it push these ones back? Like, is this one logically connected with this? So if this one gets delayed, say by 2 weeks, gets delayed to this point, does this one have to get delayed too? because it has to wait till this finishes. Now it's like this, and so now we can't start until then. It doesn't tell us that. There's no information about how changing start delivery time of one affects the others. Sometimes you'll find a hybrid methods which show both, but in its original form, it doesn't show anything about it. So here's a case of a Gantt chart, and again, it doesn't tell us, like, if I push this back by a month, is it going to push this guy back? Okay? We can have hierarchical Gantt charts. But what I'm going to focus on here, in the brief time allotted to us, is the critical path method. And the critical path method, in contrast to Gantt charts, originated good 40 or so years later. And you'll find all different variants of this. I used to cover this in greater detail, give 2 or 3 lectures on it here. I'm going to only characterize it at a high level, but I expect you to know the basic algorithm behind it. Okay? So here's a Gantt chart. Here are 2 forms of, here's a Gantt chart here. And this is a critical path method, diagrams of 2 different sorts. The basic idea, folks, is that we represent using a graph, a network. We represent tasks and their dependencies. What depends on what? And the nature of the tasks. And we can draw this in 2 different ways, and you'll find it drawn in 2 different ways. In one case, we draw the activities on nodes. This is called AON, activity on node. Sometimes called a bubble diagram. And this is the dominant method now. Occasionally you'll see this, where the activity is on the arrow, and the nodes here represent sort of instance in time where something is finished up and we're about to start a new activity. That's what's called an AOA diagram, activity on arrow. Okay. I'd like to talk about the basic ways we use these diagrams, because these diagrams are very different from Gantt charts. We define the elements of the diagram, and then we're going to run an algorithm. It's typically not us directly. It's a computer does it. Anyone here use tools like Microsoft Project or Primavera Project Manager, PPT? Incredibly common out there. So much so that I think just about every medium and large size company is going to have some. I mean, one of the most popular sorts of things used in community. Okay, so what do you need to run this algorithm? What are they going to take in? What are they going to take out? Well, you need a couple things. You need identification of activities. What are the tasks that have got to be done? And for each, you'll estimate at least one quantity in the duration. How long is it going to take? Where might we get the duration of the task from? From the estimate. Those were the estimates. Okay? The duration. Sometimes you attach dollars or other resources like people or test machines, particular test hardware, etc. to them as well. But the main thing I'm going to focus on here is duration. Okay? And then you define the dependencies between the activities. What depends on what? When I used to give this lecture in much more detail, I would have talked about several types of dependencies. Start to start, start to finish, and finish to start. In this case, when we talk about finish to start, A must finish before B starts. That's the most common. We have to finish the setup of the test machine before we can run test cases on it. The web server has got to be set up before we can do a deployment to it. The DMZ has to be set up before we can allow our external clients to test to do an acceptance test on the system on the web server. These are all examples of finish to start. You've got to finish A before B can start. Does that make sense? Okay. So we have to define the activities, do tasks, we have to define their durations, and we've got to define the dependencies between them. And then we're going to perform the CPM scheduling algorithm. if you're considering sort of resource usage and cost, you may want to further impose dependencies and refine things if it's unacceptable. For now, we'll just be talking about the single algorithm where we perform CPM scheduling. And what does it tell us? It tells us for each task in our diagram, 4 things. The earliest time it can possibly start, given all the things it depends on, the earliest time it can finish, given all the things it can depend on. The latest time it could start without risk of delaying the entire project, and the latest time it could finish without delaying the entire project. 4 things. I give them names. Early start, early finish. What's the earliest we could start it, given all the things it depends on? The other 2, late start, late finish. What's the latest it could start without delaying our entire project? And what's the latest it could finish without delaying our entire project? Okay? So in this case, the thing's they're gonna play a giant role are these dependencies. What depends on what? Okay? And the idea here is unless we impose a constraint between A and B, they can be performed in parallel. We don't have to, but they could be performed in parallel. Okay? We're going to be using this activity on node method, which goes by various names. Precedence diagram method, PERT charts are associated with it, bubble diagrams, etc. So this is an example of it. Okay, we have this project, and we're going to, in parallel with development of the system by 2 developers, we're going to have a help system developed and some people work at internationalization to turn the make sure the text strings are available in 3 different languages. The developer A is going to be developing their piece. Developer B is going to be developing their modules. They're going to do unit testing of each of them. Then they're going to, and any debugging. They're going to then integrate them, test them all together. They're going to test it in various languages to make sure it flows okay. Integrate with the help system, test further, and then they're going to burn it onto media, or they're going to make it live, or what have you. People comfortable with this sort of idea? These are tasks, and a dependency here, for example, between this dev A and test A means this task has to finish before this one can start. Does that make sense? Okay, so imagine that for a small, it's a very simplified example, a small example. We could also depict the same thing using activity on arrow diagram, but we're going to make use of activity on node diagrams as our main way of doing it. Okay? Okay, so what's the CPM algorithm that's the core of this method? Well, it takes as inputs tasks, typically names as well, some sort of identity of the task. In any case, the duration and dependency. I think I'll modify that here just to say it's name, because typically we label the tasks in a nice way with their names. Durations and dependencies. What depends on what? And again, we're going to calculate early and late, finish and start. Or no, so it's 4 things. For the Cartesian product of all 4 of those things. Early start, early finish. Late start, late finish. Burn that in your mind, folks. Seems each year I ask them to find close to that. And sometimes I get back blank. Doesn't feel anything. Nothing. Just remember that. Early start, early finish, late start, late finish. And know what they mean. So early start, early finish, again, is earliest we could start or finish given other tasks that we have to do first. Before we can start this task, we've got to get some things done. Given that, what's the earliest possible time we can start this task? You wake up in the morning. The team's going to meet. People contact you, text you, and they say, when can you meet? Wherever you are. So you're bus. This time. Well, the earliest we could meet these late finish. The latest you could finish or start this activity without delaying the whole project. Let me repeat that. And forgive me, but students can get these wrong. Late start and late finish. The latest you can start or finish without delaying the entire project. You could start or finish this particular task without delaying the project. And I want to emphasize, these are not the latest you could start or finish, and still be having kept busy with other activities. It's without delaying the project. So we illustrate these things on diagrams that use a variety of mechanisms. Primavera, for example, PPP uses this one here. This is a way we'll be using in an exercise. Okay, so there's two passes to this algorithm, folks. Pass one is a forward pass. It's going to determine the early start and early finish. It's going to be common sense. But you got to think if you're systematic. It's going to have a lot of intuition behind it. But if you're not thinking clearly about it, you can forget that and end up misremembering. So the forward pass of this is going to determine early start and early finish. And the idea here is because all preceding activities must finish before successor. If A depends on B and C, it can only start after the maximum of the finish times of B and C. Does that make sense? If I can only start debugging this after my personal machine is set up and the database server is set up, then I'm not going to be able to start debugging this until both of them are done. In other words, I can only start debugging at the maximum of the times that setting up the database server and setting up the test machine is complete. Does that make sense? Okay, good. So that's the forward pass. And the overall project duration is defined as the maximum to the early finishes of all the nodes in the project. Then there's going to be a backwards pass, okay? Going back from the finish of the project. And basically the idea here is we're deriving late start, late finish, okay? And the idea here is because preceding activity must finish before any following activity. The late finish of a given activity is the minimum of the late starts of the following activity. If you folks are depending on me to finish your jobs, and the latest that you can start without delaying the project is, 10 o'clock for me to be there to finish my stuff, then I've got to finish no later than 10 o'clock. Maybe one of you has got to get started by 9 o'clock for you to get ready for the demo. And in which case, I've got to finish by 9 o'clock, the minimum. The latest I can finish is determined by the minimum of the times you folks can get started. Okay, so we use these things all the time in our reasoning. And you just got to realize this. It's common sense when you think it through. So the forward pass here is, okay, it's 8 a.m. You want to know what's the earliest time you can arrange to meet your team after performing this test. Suppose you have a shower to take, you want to boil some water in a water heater, you want to eat breakfast, and then you want to walk to campus. And each of them has some time associated with it. Remember, these are the inputs. What's the earliest time you could meet your team? I've artfully left some information out here, and that's to give you a clue. What's the earliest time you could meet your team?
15 minutes from start.
Okay, and a great focus. And how did you get that? Okay, great. So add 5 to 10, 15, 20, get 50, right? Good. But can anyone raise a question about that? Yeah. Yeah. Why don't you take a shower and boil the water at the same time? Maybe you can even eat breakfast while walking to campus, depending on what it is. Well, if it's in a bowl, it might be harder, but people have been known to do that. So if we can do some things in parallel, we could do it sooner. Do you understand that? So suppose we can take a shower and boil water at the same time. Then what's the earliest time we can get to campus? From 45 minutes. Because these things overlap. You can't eat breakfast until the what of these two? the water is boiling because that finishes, it's the maximum of the finish times of both of these. This finishes after 5 minutes, this finishes after 10 minutes, right? And we can't start eating breakfast until the maximum of that. We're going to be waiting for one or the other. In this case, it's for the water. So we take this maximum all the time in our intuition. Another one, here's the backwards path. You do this all the time. Suppose your plane's going to leave at 12 p.m. from the Sassaman Airport. You need to know what time you're going to get up to make the plane. And you've got to take a shower, boil water, eat the breakfast, call, wait for a cab, take the cab to the airport, check in, and sit on the plane. And suppose that these are the times you're confident are enough for each of them. By what time should you set the alarm? Well, you end up doing kind of a back calculation, right? Kind of say, well, the plane's got to take up like, so let's see, I have to be, sitting on that plane by 20 minutes before that. So I have to check in 20 minutes before. Don't go in, this should be like an hour before. Don't trust this. Don't use this to guide your life as to how to catch a plane. So you got to be, 40 minutes before you got to be there checking in, right? So that's 11:20. You got to take the cab to the airport no later than, well, I'm going to call it home. Don't do this, okay? You got to call and wait for the cab 20 minutes before that, so 10:40. You got to eat breakfast starting 15 minutes before that, 10:25. And then taking a shower or boiling water, well, if you could do them in parallel, right, you might be able to start taking the shower, for example, you might be tempted to start, say you could take it at 10:20, but you've got to start the water boiling before that. So you have to get up and no later than, I think it's 10:15, I think, because you've got to get the water boiling to heat eating breakfast to avoid delaying the plane. Okay? So in other words, you've got to get up according to the minimum of these two taken when you have to start taking the shower or boiling the water. Whichever one is kind of the key one, that the key constraint to let you finish on time. In this case, it's boiling the water. Okay? Okay, so let's talk about this. Suppose we have a little project like this, and this is all we're going to have probably time to do here. So we have a little project that involves these steps, okay? So I want you to figure out for me the early start, early finish, late start, late finish associated with each of these activities, okay? So let's draw this. I'll draw this out here, and we've got something like that, and here, and then we've got two here, something like that, and then this guy is down here. We've got two tasks out here, and so on. And each of these has these sort of diagrams on it. Okay, so we're going to fill in early start, early finish, late start, late finish. This would be early start, early finish, late start, late finish for each. Suppose we start at time 0. Okay, the duration of the activity is shown on the lower side here. So what's the earliest start we can start this one? What's the earliest possible time we could start? Time 0. What's the earliest time we could finish it? Time 2. Earliest start time we could start this one? 2. Earliest time, so let me fill this in so it's on the diagram there. Is this 6 here? And 4, 4. Okay, so this is 2. So the earliest time we could finish this? 9, good. Okay, this guy here, what's the earliest time we could start him? Yeah, he only depends on this one, right? Don't be fooled by the split here. He only depends on this one here, right? What's the earliest time it could finish? 11? 11 days? Yeah. What's the earliest time this could start? 11, finish. 13, start. 13, finish. 19. Okay, great. And now let's go this lower path here. So what's the earliest this guy can start? 9, earliest he can finish. 13, earliest this guy could start. 13, and then 17. You'll notice when you're going down straight line paths, it's really easy. You just copy the last one. As long as there's no join points when they come together, makes it really easy. Okay, now, ladies and gentlemen, excuse me, so this guy doesn't join up with this one, it joins up with this one. So what's the earliest time, given that to finish the project we have to finish both the upper and the lower components of it, what's the earliest time we could finish this? Yeah, the earliest time would be 19. Okay, and this upper one is sort of the limited one, right? So that's great. Okay, given that we could finish it at time 19, what's the latest time that we could start, for example, excuse me, the latest time we could finish this lower one here and still finish the whole project on time? 19. We have some slack, we have some latitude here. We could finish it as soon as 17, but we don't have to, right? We have some give. Does that make sense? We could actually finish it as late as 19. It's not going to delay the whole project. Why not? Because it's waiting on the other task. We could finish this at time 17. We could work our butts off to finish it at time 17, but we don't have to. We still are going to wait 2 more days for this guy. Okay? So finish it. So the latest that this could finish would be time 19 without delaying the whole project. What's the latest it could start then? 15. What's the latest this guy could finish without delaying the whole project? 15. What's the latest he could start without delaying the project? 11. Okay, good. I am going to work, for reasons that will come clear later, on the upper path now. What's the latest time this guy could finish? The upper guy, the upper right. 19. He has no leeway. We don't have slack here. We have really no latitude in terms of when the earliest he could finish it is the same as the latest he could finish. We got to keep on the ball with this one. What's the earliest he could start without delaying the whole project? 13. Okay, this guy here. 13. This 11. 11. 9. Okay. Now, this is where it's at. Now, we got to merge in. On going the first pass, you're worried about joins coming together. Here, you're worried about, splits going if you look forward or joins going backwards. So, ladies and gentlemen, what's the latest time we could finish this project, this task here, the second task in my whole list, without delaying the whole project? And why is it 9? Why is it not 11? Suppose we finish at 11. What bad thing would happen? It would delay the top one. And this guy has to start by 9, the guy to his right, to finish the project in time, right? So the latest this guy could finish without delaying the whole project is the minimum of these 2. You get that? Yeah. And so the latest this could start would be 2, and the latest this guy could finish would be 2, and the latest he could start would be 2. Ladies and gentlemen, we've just run the CPM diagram for this. On the forward paths, we ended up taking the maximum. Remember, this 19 was the maximum of this 17 and 19 here? So when things come together, joins occur, we take the maximum. Going backwards, we took the minimum of these 2. Because we've got to finish this by the time needed by any of our successors, right? This guy needs it by 9, this one by 11, but we got to finish it by 9 in order to finish the whole project. The late start of our successors, the minimum of them is our late finish. So it's 9. People appreciate that. Forward pass, maximum of predecessors. Backward pass, minimum of successors. But ladies and gentlemen, the key thing here that I want you to take, if there's one concept I want you to take away from this lecture, it's this. This is what's called the critical path of your project. It's called the critical path because we have no give, we have no leeway, we have no float, we have no flexibility. This is the path. These are the set of tasks in the project, this upper path, where if we don't hit each one and keep on the ball with each one, we're going to be delaying the whole project. This lower path, we have some slack on. We can actually delay like 2 days this thing. Not be on the ball particularly with it. We could shift people from this component onto here to speed this up, the upper path if needed. This lower path, we have some give on. We don't have total give. If we delay it by 3 days, it will now be the critical path. But we have give on it. We have 2 days of give. And as a project manager, those on each team will need to focus on what is the critical path to get us to where we need to go for this incremental delivery. What do we have to just hit on consistently, and what do we have slack on? What can we kind of lay off on without having to worry much, and what things are going to screw us over if we lay off? Do you understand that? Okay, so identifying a critical path is something that I would expect each project manager to try to do for each incremental delivery. Think through, okay, what things have got to get done, what are the dependencies between them, and which of these tasks, therefore, do we have to get on the ball right now? Maybe it's contacting the client, you know, getting an appointment with Jenny Basran, because that may take 5 days to make, and if we do it next week, you know, we'll be a bad way because it probably won't come together by the final incremental deliverable deadline. Because after we speak with her, then we need to do X, Y, Z, and there might not be time. So you should be thinking, what is the critical path? What are the things we can't screw up on? And therefore, give those things a special attention. Privilege those things in terms of your focus during the project, because that's where it will matter. And furthermore, you should be attending to, if the critical path shifts at some point, you'll catch that fact. So the final thing I'll just say here is there's a concept of float or slack, and I mentioned it earlier, and it's in its simple form, it's the early finish minus the early start. Late finish, late start minus early start, late finish minus early finish. It's going to be the same thing for the simplified case we looked at. And I mean, for the simplified version of this we've been looked at in general. It's not based on this particular value. But in this case, we have slack of 2 because the 11 minus the 9 or the 15 minus the 13 is 2. This upper path has slack of how much? 0. That's the definition of a critical path. The longest sequence from start to finish of 0 slack, 0 float. We also use the word tasks. And there's going to be, based on the algorithm we saw, there's going to be some path of that, at least one. And you find the longest one associated with it, 0 float, that's going to be a critical path. Make sense? That's how you'd identify it. You'd look for 0 float paths. Okay, that's all for today. Thanks very much. And have a good break. We're going to be delaying the